Welcome to random series CSER, JRF, NET set and HSST examinations. Today we see a few questions from quantum statistics. And this is class number R11. Questions from quantum statistics. And here is the first question. Two questions are written here. Only we have to remember the answers, and these things you study in your theory classes. The first question is, the spin-Sir boson is equal to positive integer, positive integral multiple of half any fraction. The spin-Sir boson is equal to positive integer, b integer, c positive integral multiple of half d any fraction. So you remember the answer is integer. The boson spin is 0 or any positive integral values. So the answer is integer. Not alone the positive integer, 0, 1, 2, etc. So it is better to write the answer B, integer. Second question, the distribution function for a photon is. The distribution function for a photon is, you remember a photon is a boson. Photon is a boson. The distribution function is e raised to minus epsilon by kt, b 1 by e raised to or exponential e epsilon by kt plus 1, c 1 by exponential epsilon by kt or e by kt minus 1, d 1 by exponential minus epsilon by kt minus 1. And you remember the answer is B. This is Boson's own Bose-Einstein statistics distribution law. In the equation you remember Ni by Gi. Ni by Gi is equal to 1 by e raised to alpha plus beta epsilon I plus 1 minus 1. That you remember. The Bose-Einstein distribution law is Ni by Gi is equal to 1 by e raised to alpha plus beta epsilon I minus 1. And Ni by Gi is called a distribution function. B distribution function Ni by Gi, we call it as Fe. So F is equal to 1 by e raised to alpha plus beta epsilon I. Alpha is taken as 0. So beta is 1 by kt. So e raised to 1 by e raised to e by kt or epsilon by kt. Energy we can write as epsilon. E raised to 1 by kt e minus 1. Answer is C. You refer Bose-Einstein distribution law. Next question. For a two-dimensional free electronic gas, the electronic density N and the Fermi energy EF are related by, you remember it is a two-dimensional free electronic gas, not a three-dimensional. For a two-dimensional free electronic gas, the electronic density N and the Fermi energy EF are related with the relation. And you know, the Fermi energy relation we have studied is equation number 1. And here it is for two-dimensional free electron. So when we reduce it, we get answer C. Next question, the specific heat of an ideal Fermi gas in 3 dimensions at a very low temperature T varies as. Answer A, it is T raised to 3 by 2, T square, T raised to 3. The answer is T. The specific heat of an ideal Fermi gas in 3 dimensions at a very low temperature T varies as T. Next question. Which of the following given condition for a stable equilibrium of a thermodynamic system? Which of the following gives condition for stable equilibrium of a thermodynamic system? ഒരു തെർമോഡൈനാമിക് സിസ്റ്റത്തിൻ്റെ സ്റ്റേബിൾ ഇക്വിലിബ്രിയം കണ്ടീഷൻ എന്താണ്? Which of the following gives the condition for stable equilibrium of a thermodynamic system? A. D is equal to 0, D is equal to 0, and D square is less than 0. S stands for entropy. B, D equal to 0, D square E greater than 0. C, both A and B. D, none of this. The answer is both A and B, that is C. Next question. Which of the following statements is true? Fermions are distinguishable whereas bosons are not. You know, bosons and fermions are indistinguishable. So that is wrong. B, bosons are distinguishable whereas fermions are not. See, both fermions and bosons are distinguishable. Indistinguishable are bosons and fermions. D, both fermions and bosons are indistinguishable, but classical particles are distinguishable. Classical particle boson. Boson and fermion are quantum particles. Both fermions, bosons and fermions, they are indistinguishable particles. Answer D. Next question. The spectrum of radiation emitted by a black body at a temperature 1000 K peaks in the spectrum of radiation emitted by a black body at a temperature 1000 K peaks in the visible region of frequencies, infrared region of frequencies, ultraviolet region of range of frequencies, microwave range of frequencies. അപ്പോൾ ഇവിടെ ഈ 1000 കെയിലാണ് 1000 കെയിലെ ഒരു ബ്ലാക്ക് ബോഡി സ്പെക്ട്രം അത് മൈക്രോവേവിലാണ് കാണുന്നത്. മൈക്രോവേവ് ടെമ്പറേച്ചറിൻ്റെ സ്പെക്ട്രമാണത്. നമുക്ക് വിയേഴ്സ് ഡിസ്ട്രിബ്യൂഷൻ ലോ വെച്ച് കണ്ടുപിടിക്കാവുന്നതാണ്. ഓർ വിയേഴ്സ് ഡിസ്പ്ലേസ്മെൻറ്റ് ലോ അത് വെച്ച് കണ്ടുപിടിക്കാവുന്നതാണ്. അടുത്ത ക്വസ്റ്റ്യൻ. ഇത് ടെമ്പറേച്ചർ ഓഫ് എ ക്യാവിറ്റി the temperature of a cavity of fixed volume is doubled. Which of the following is true for the black body radiation inside the cavity? The temperature of a cavity of a fixed volume is doubled. Which of the following is true for the black body radiation inside the cavity? A, its energy and the number of photons both increases 8 times. B, its energy increase 8 times and the number of photons increase 16 times. C, its energy increase 16 times and the number of photons increase 8 times. D, its energy and the number of particles, number of photons both increase 16 times. And the answer to that question is C. Answer to that question is C. That is, its energy increase 16 times and the number of photons increase 8 times. Next question. Consider black body radiation in a cavity maintained at 2000 K. If the volume of the cavity is reversibly and adiabatically increased to 10 cm cubed to 640 cm cubed, the temperature of the cavity changes to. Consider black body radiation in a cavity maintained at 2000 K. If the volume of the cavity is reversibly and adiabatically increased from 10 cm cubed to 640 cm cubed, the temperature of the cavity changes to 800 K, 700 K, 600 K, 500 K. ഒരു ക്യാവിറ്റിയിൽ റേഡിയേഷൻ ഉണ്ട്, ടെമ്പറേച്ചർ 2000 ആണ്. ആ ടെമ്പറേച്ചർ മാറ്റുകയാണ് അഡിയബാറ്റിക്കലി റിവേഴ്സിബിളി. വോളിയം 10 cm ക്യൂബിൽ നിന്ന് ഇൻക്രീസ് ചെയ്യാണ് 640ലേക്ക്. ടെമ്പറേച്ചർ എത്രമാത്രം ചേഞ്ച് ചെയ്യും? ആദ്യത്തെ 800 K, B 700 K, 600 K and 500 K. Answer. According to V's displacement law, TV raised to 1 by 3 is constant. So we arise as two cases. And this is V's displacement law connecting temperature and volume. So T1 V1 raised to 3 is T2 V2 raised to 1 by 3. T1 V1 raised to 1 by 3 is T2 V2 raised to 1 by 3. T1 is 2000 K, V1 is 10 centimeter cubed, V2 is 4 centimeter cubed, and we have to find T2. We have to find T2. Hence 2000 into 10 raised to 1 by 3 is 40 raised to 1 by 3 into T2. That is T2 is 2000. You write it 2000. 2000 into 10 by 640 raised to 1 by 3. And you can easily calculate without a calculator. You can calculate 10 at will cancel 1 by 64. The cube root is 4. 2000 by 4. That is 500 K. So when we write the last step, T2 is 2000 into 10 by 640 raised to 1 by 3. So answer is 500 K. That is all with your 11th lecture on quantum statistics, CSIR, JRF questions, net questions. Thank you very much.